Hello, and welcome to Aggressive Physics. Today is day 81, and what I'd like to do today is look at the interference of waves. Now, waves try to occupy the same space at the same time, and they're going to interfere with one another. So what we do is we have a situation where the waves, although they are vibrating particles in a piece of air or possibly water or some other material that's elastic, they'll try to pull on the particles in different directions. And we call that interference. And when the two waves try to pull the object together, we're going to get a bigger resultant from that. And if the two waves are going to pull in two different directions, they're going to oppose one another in terms of the force and sometimes produce a state of equilibrium, or at the very least, a state where the vibration of the object is less than it would with only one wave. So waves try to occupy the same space at the same time, and they can because they pass through one another. However, while they're on top of each other, they're going to interact with the particles in different ways. Now we have a fancy term for the resultant of the two waves pulling the objects or the particles themselves, and we call that superposition. And what we basically do is we add up the forces acting on the particles from all the waves that are at the point of contact. And when we add them all together, we get the answer, which is the resultant that the particle will move. But instead of just calling it the resultant, we call it the superposition. So the particle will be at the final position depending upon how the different waves interact. So for example, just numerically, if we had a wave that's going to pull a particle up with a single unit, it could be centimeters or meters, and another wave tries to pull up with the same 1 meter or 1 centimeter, then the resultant of that would be two 1-ups or 2. So the particle itself would move a total of 2 centimeters or meters or whatever the unit is. On the other hand, if another wave comes through and wave 1 tries to pull up on the particle with a 1, and the other wave tries to pull down on the particle with a 1, the resultant would be 0 because we would subtract the 2. So the superposition is the final placement of the particle due to the interaction with the two waves themselves. Now, when we have waves that combine and form a bigger wave, we have a term for that, and we call it constructive interference. Constructive because it's getting bigger. So if we have wave A traveling and wave B traveling towards one another, and they both produce crests, when those two crests interact, they're going to form a bigger crest that's going to be the sum of A plus B. Now the units don't have to be the same. In fact, the frequency doesn't even have to be the same, or the wavelength doesn't have to be the same, and you can have wave patterns that are quite complex. But for most of our practice problems, we're going to deal with two waves that have similar widths, so they're going to have the same wavelength. And then the amplitudes may be different, and the amplitudes may point in different directions. So for example, if A is 1 and B is half, the superposition of the particle when they're combined would be 1.5. And it doesn't always have to be whole numbers. Like I said, it could be fractional values as well. But either way, when the waves combine and form a bigger wave, we're going to call that constructive interference. When we have constructive interference, we consider the particles or the waves to be in phase with one another. When they're in phase, they're going to combine positively. Now, if they're out of phase, we have a crest and a trough trying to pull on a single particle. We're going to call that destructive interference. And when we have destructive interference, one wave pulls up on the particle, one wave pulls down, and the resultant is the difference between the two. Now, the difference doesn't always have to produce equilibrium or 0. It could be that one of the waves is stronger than the other. And in that case, the winner would be the one that has a larger value. So if a crest is pulling up with 1 and the trough is pulling down with a half, the winner in this case would be the crest, and the resultant would be a positive waveform with a half of an amplitude. Now in that case, the superposition would be positive a half. If it were the trough that had a 1 and a crest with a half, we would have a superposition of a negative 0.5 or negative 1/2, and that would produce a trough. So it all depends upon the size of the waves that are interacting. Typically, though, what we do is if they're together and they're in phase, two crests come together or two troughs, we add them. If we're out of phase, we have a crest and a trough coming together, we subtract the two. When they add together, it's constructive interference. And when we subtract them, it's destructive interference. Now, an example I like to use for constructive interference is when, in most elementary schools, the kids took out the big parachute during their early years in school. And if you ever did that, what happens is, to refresh your memory, you had the class standing around this big parachute, and the entire class would shake the parachute together, and it would produce this big wave in the center. And what you're basically doing is learning constructive interference at an early age. The teacher or the instructor would probably count down 3, 2, 1, go, and all the students would pull the parachute in the same direction, probably up then down, to produce a wave traveling towards the center. Now, what's interesting is some of the kids were probably stronger than others, so the crests were bigger for some of the kids. However, the speed of all the waves is the same. So when you had a class of 20 kids sending crests to the center of this wave, it's going to produce a super big waveform in the center, a big crest. And if you did this in gym class, probably what happened was the parachute floated up towards the top of the ceiling and then settled down on all the kids. Sometimes you'd lay down underneath and have it rest on you kind of like a blanket or a comforter. Other times you'd have kids try to run in between before it caught them in the middle. Either way, if you did that all together, 3, 2, 1, go, you would send the waveform to the center at the same time, and all those mini waves, 24 little kids can't produce a really big wave, but when they combine together, you form a big constructive interference zone in the center, and it filled up the entire parachute. So that's a classic example of constructive interference. And if you haven't done that and you have access to a parachute, I suggest you get a couple of friends together and you try it. It doesn't really work as well with a blanket or a comforter because they're not as large. The parachutes are quite big and it produces a much more visual effect at the end. If you did have some of the kids not go at the same time, what would happen is you'd produce some destructive interference and possibly the wave wouldn't be as big as it could have been. So if you have 24 little mini waves coming in and 5 or 6 of them were in the wrong direction or out of phase, you'd have a situation where most of the class was in phase and produced a constructive interference, but then a few of the waves were the opposite and subtracted from the total value. So it only worked fully when the entire class was coordinated and synchronized. But that's a good example of constructive interference. Now, that being said, if we have a situation where we have 2 sound waves producing the same note, possibly from a signal generator, what we can do is have a situation where all the waves, because they're being produced continuously, will interfere in predictable patterns. And what happens is you have areas of constructive and destructive interference. And with the slide we're looking at now, you can see that the circular wave patterns produce an X-type pattern when they're destructively interfering, and they combine and move on top of one another when they are producing constructive interference. Now, we have fancy names for the lines that produce constructive and lines that produce destructive interference. If it's destructive interference, we call them nodal lines, and that's going to be important when we talk about standing waves in tomorrow's lecture. If we have constructive interference, we call that anti-nodal lines. So it is possible if we produce a single wave note from a signal generator and we have 2 speakers near one another, that you could walk across the room parallel to the speakers' configuration themselves and actually have areas where you hear the sound loud and soft. If you were to do this outside because there's no echo or reflection of the sound waves in the room, you could have a situation where all of the sound waves where it's a nodal line are completely silent, and all the sound waves where it's an anti-nodal line are loud. So the bottom line is where it's anti-nodal, you have constructive interference, and where you have nodal, you have destructive interference. And this is produced when we have a continuous waveform. With the example of the parachute, it was a single pulse that we sent. If you have a signal generator producing a single note, what will happen is you'll have a continuous wave or a periodic wave, or even if you want to call it a wave train. And that will produce nodal and antinodal lines that are constant and continuous. So if you have access to this, that would be something that you could try. You could produce a single note with two speakers, put them as close as you can together, and then walk across the room parallel to the speakers or perpendicular to where the wave's going out the center, and you should hear areas of loud and soft sounds. Where it's loud, you're going to hear antinodal lines, and where it's soft, it's nodal lines. So that's the difference between constructive and destructive interference. Now that's all I'd like to talk about for today. Today was about interference of wave patterns, and we'll look at standing waves starting tomorrow. This was Mr. Predwicki in Agrosive Physics, and I thank you. All right, as we discussed earlier, interference has two different types. We have constructive and we have destructive. When we have constructive interference, that means the waves are in phase. So if we have two waves traveling towards one another, and there's both crests approaching, when they meet in the middle, they'll form a larger wave, which will be the summation of the amplitudes of A plus B. We call that the superposition. Now, unlike particles, though, as they travel, they will continue once they collide to travel in the same direction that they originally were moving in. So B will travel to the left, and A will continue to travel through the right. So they pass through one another, collide in the middle, and then just continue on their merry way. On the other hand, we have destructive interference, and that's when they're out of phase. So we'll have a crest coming in and a trough coming in. And we'll have A as the crest and B as the trough. Now, when they collide, if they're the same size, they'll produce nothing. It'll be flat at that spot. However, just like with constructive interference, after they interfere with one another, B will continue to move to the left, and A will continue to move to the right. So they'll continue on their path. And once again, this is the superposition. Where they collide, we combine the amplitudes of both waves. So A would be a positive, B would be a negative, so you'd subtract the two. With constructive interference, both are positive, so you add. If two troughs were coming together, it would be the combination, but it would be on a negative direction, so it would be a trough. But that's interference at its most simplistic manner. The previous example showed two pulses colliding. With constructive interference, you had two crests, and with destructive interference, you had a crest and a trough. Now what I did here is I have a transparency that has a number of concentric circles, and that shows periodic wave motion. And it's hard to see because they're so small in terms of the circles, but there's a number of circles on this transparency. Now if we take a second transparency and overlay it upon the first, what we can do at first is take them and put them on top of one another. Now the way this works is every circle represents a crest, and every light area in between the circles represents a trough. Now as I separate these patterns, you'll see that the pattern that's produced with the two transparencies changes. This is almost an optical illusion that you might see on a poster or something like that. Now, the dark areas, like here, are where a crest and a trough are coming into contact. So these are zigzag patterns where a crest and a trough collide. The lighter areas are where crests are on top of crests, so the circles are on top of the circles, and the blank areas, which represented the troughs, are on top of the troughs. Now what this produces is areas of constructive interference in the light areas and destructive interference where it's dark. So we have constructive and destructive and constructive and destructive and constructive and destructive in this area. As I separate the two sources, you'll notice that the pattern changes. And we can figure out this mathematically, and we'll talk about this a little more later in the light chapter. but these areas change in terms of their width. Now we have fancy names for the areas of constructive interference and destructive interference. If it's constructive, we call it anti-nodal. If it's destructive, it's called nodal. And this will be important when we discuss standing waves. Now, in terms of a practical application of this, if we have two speakers that are producing notes and we want them to fill in the sound throughout the room, we're going to want to separate them as far away as possible, because destructive interference or nodal lines actually produce little or no sound. So you could have areas of dead sound in a room. If we put the speakers really close together, you can have these big areas of destructive interference. As you separate them, you'll notice that the pattern is almost smushed together. The areas of constructive and destructive interference are lessened in terms of their width. Now what that means is if we separate the speakers throughout the room, we're going to produce a pattern, even if they do interfere, that's too small to be noticed, because a person having ears on both sides of their head will hear the sound. So this is, as long as it's smaller than a human's head width, it won't produce dead area in a room. Now, of course, we also have echoing sound, so the reflection of the sound waves bouncing off the walls will fill in these nodal areas. But typically what you'll notice is that speakers are separated as far as possible in a concert or in a lecture hall or something like that, in order to cut down on the dead air and the dead space. It's using physics to avoid seats that have bad sound. So that is a periodic wave situation. If we keep the speakers really close together, we're going to have big areas of constructive and destructive interference. And if we separate them, the pattern will change and be much smaller. Constructive interference is antinodal, and destructive interference is called nodal. And these lines are spread out from the sources.